In this video, we will walk you through a detailed step-by-step procedure for modeling and analyzing a 4-story steel brace frame structure using Tectonus DMAX braces in ETABS. DMAX brace system is a passive damping system which reduces the response of the structure without any damage or yielding of the elements and can be tuned for various levels of initial stiffness as per the required performance of the building. These innovative braces are designed with a non-degrading load deformation response, making them an ideal load damage solution to resist the lateral load imposed on a structure during an earthquake. This video will demonstrate how to effectively implement the DMAX with brace frames in ETABS. For modeling, the designer has selected a 3-bay steel structure, each bay spanning 6 meters with the total height of 15 meters. The ground floor stands at 4.5 meters, while the upper floors are 3.5 meters high. The lateral load resisting system incorporates Tectonus DMAX braces in a chevron configuration placed in the central bay to improve the structure's performance against lateral forces. The gravity loads applied on the frame in terms of UDL load consist of the dead load of the slab and the metal deck, exclusive of the self-weight of the structural members, the superimposed dead load, the live load, and the facade load at level 1, 2, and 3. The designer has adopted a target ductility factor of 3 for the structural design of this 2D frame. It is important to note that all nonlinearity will be concentrated on the Tectonus DMAX, while the structural members will be designed with an overstrength factor of 1.15 for the DMAX, ensuring that the members remain essentially elastic when the frame is subjected to lateral loads. The first step in implementing DMAX in this 2D model in series with the braces is to estimate the peak demands in the braces at each level. To estimate the axial forces in the braces, the designer must estimate the lateral forces at each level using equivalent static method. In this case, the lateral forces calculated and applied on this model in the global y direction is shown. At level 1, we have 250 kilonewton, followed by 450 kilonewton at level 2, 740 kilonewton lateral force at level 3, and 780 kilonewton at level 4. Once the forces are applied at the respective level, we will then run a linear static analysis to estimate the axial tension and compression force in the braces. To do that, we will go to Analyze, Set Load Cases to Run. We will run the earthquake Y because the frame is modeled in global Y direction and the height is in global Z direction. So we will run the analysis to estimate the maximum axial forces in the braces at each level. Once the analysis is complete, you will click on Display Frames and then go to Axial Forces in the component. Select the load case EQY, earthquake in the Y direction that we have applied the lateral forces at each level. Then click on Apply. So doing so, you will be able to see the magnitude of the axial force on the braces at each level. So if you right click on that member, you will be able to have a look at the maximum brace force in terms of axial tension or compression. So looking at the analysis result, we have 2005 kilonewton axial tension and compression at level 1. Level 2 is 1505. Level 3 is 1164. And at level 4, it's 601. So we will use these brace forces, the maximum forces, to size our DMAX. So at level 1, we have 2000, level 2 is 1505, level 3 is 1154, and at level 4 was 601 kilonewton. So we will size the DMAX for these braces So we will size level 1 DMAX to be 2000 kilonewton, level 2 to be 1500, level 3 1100, and level 4, let's say 575 kilonewton. Once you have sized the DMAX for respective levels, we will then need to define these in ETABS. It is important to note that the DMAX will be modeled as a link element in series with the braces. So we will cut one end of the brace to implement the link element resembling the DMAX. So to do that, we will make a copy of this model. So save as. We'll name this as model 2 in elastic model, and we'll make a copy of this model. Then the next step is to define the 4 DMAX that we have just specified. So we will, to define the DMAX link properties, we will go to define section properties, link properties. So we will, let's say, add a new property, and we'll name this as DMAX 2000 kilonewton for level 1 brace. The link type resembling the non-degrading load deformation response that can be used to resemble the DMAX is plastic when. The active nonlinear direction will be U1. So the link will only activate in U1 direction. The axial tension and compression of the link will only act in U1 direction. U2 and U3 can be fixed. We do not allow any deformation to occur in U2 and U3. So in U1, the designer must specify the appropriate nonlinear properties. So the force capacity of this DMAX is 2000 kilonewton at level 1. Post-yield stiffness can be specified as 0 or a very small value, 0.001 or 0.0001, considering the fact that there is no yielding in the system or in the DMAX itself. So this can be specified as 0. Yielding component can be specified as 10. The nonlinear stiffness is the stiffness at which the device slips. So this is estimated as the force divided by the slip displacement. So in this case, we will specify 2 mm slip for this device. So our nonlinear stiffness will be 2000 divided by 2 millimeter. So the unit for this nonlinear stiffness is kilonewton per meter. So we will say 0.002 meters. The effective stiffness is actually the ultimate force divided by the ultimate displacement. So our ultimate displacement at this point in time, initial design, we can specify somewhere between 40 mm to 50 mm. But after the analysis, we must come and have a look and ensure that the estimated ultimate displacement is corrected to the actual. So by looking at display link deformation, we will be able to capture what is the actual displacement of that link. So the effective stiffness will be 2000 divided by, let's say we will use 40 mm, so 0.04. Okay. Like I've mentioned, U2 and U3, we do not allow any deformation to occur in this direction. So we can specify, can leave it as fixed or specify a larger stiffness for this direction. So let's say we will specify 80,000 kilonewton stiffness in U2 and U3, considering that there's no deformation that will occur in U2 and U3. The rotation, because these links will only activate in axial tension and compression, we will have to suppress the rotation of this link. So we can ideally select all the rotations and assign a fixed regime, or the other option could be select the rotation about degrees of freedom and specify a larger stiffness for these rotations as well. And this will ensure there's no rotation of this joint. The stiffness used for linear and modal load cases, we will select this as effective stiffness from 0 else non-linear. And the stiffness used for proportional viscous damping, we will select initial stiffness. We will click on OK. So the DMAX at level 1 is now defined. We will have to repeat the same for level 2, level 3, and level 4 DMAX. So we will make a copy of this and we'll say this is DMAX. For level 2, it was 1,500 kilonewton. We will have to make adjustments to the ultimate force, so 1500. 2 mm slip. Next, DMAX at level 3, 1,100 kilonewton. So the final DMAX at level 4 is 575 kilonewton. And then we can save the DMAX properties that we have defined. So the sections are now saved. Now, in order to implement the DMAX in series with the braces, we have to cut one end of the brace. Therefore, the designer must select the appropriate length of the device to be implemented in series with the brace. The ideal length of the DMAX could be within the range of 0.7 meters to 0.9 meters. So the designer must first identify what is the actual length of the brace. So to do that, just click on the brace, right click on the brace, and then you will be able to see the actual length of the brace. So it's 5.4 meters. If you divide this by 7, then one segment of the brace will be approximately 0.77 meters. So you can probably delete one segment, which is the end segment of the brace, to implement the DMAX that we have just defined. So to do that, because level 1 is taller than the other levels, the brace at level 1 is slightly longer than the other braces. So we will see level 2, 3, 4 brace length is 4.6 meters. So at level 1, we will divide the brace into 7 segments. At level 2, 3, and 4, we will divide the brace length into 6 segments. The reason is this is the fastest method in which we can cut one end of the brace to implement the DMAX in series with the brace. Now, once the end segment has been deleted to implement the DMAX brace, the designer must ensure to join the members to ensure there's no instability during the analysis. So you could probably go to Edit, Join Frames, and select the frames to join them together. So once the frames has been joined, we will assign releases we release the bending moments about the major and the minor axis, because to ensure that the brace is acting in tension and compression, and the joint is also not taking any moment. So we will select the frames, we'll go to assign, frame, releases, and we will release the moments about 2, 2, and 3, 3, the major and the minor axis. Once this has been done, we can then draw the link element representing the DMAX at respective levels. So at level 1, 2000 kilonewton, we will go to draw link elements. We will select 2000 kilonewton DMAX, and we will draw the DMAX at the end of the brace in series. Level 2, 1500 kilonewton. Level 3 is 1100 kilonewton. Level 4 is 575 kilonewton. Now, once we have implemented the DMAX in the form of modeling the link elements in series with the brace, the last step will be to investigate the seismic performance. So to do that, we will run a nonlinear static pushover analysis at 1.5% drift to verify the seismic performance and to develop the cyclic pushover curve for this 2D frame. So before we define the pushover load cases, it is important to know two things. One is the direction in which we will be running the pushover, because this model, as I've mentioned earlier, is developed in a global Y direction along the length of the frame, and the height is in global Z direction. We will need to run pushover in Y direction. So in pushover analysis, we must select U2 rather than U1. If the frame was modeled in X direction, we will have to select U1, and I will show you as I go along, showing the next part of this video. So we will push the structure at 1.5% drift, so to the total height. So we will click that node. So that will be our reference node for the pushover analysis. The label of this node is 4. If you can see here on the screen, the unique name is 24. The label for this joint at the top right is label 4. And the total height, as you can see, global Z, that's 15 meters. So 1.5% of 15 meters is 225 mm. So we will push the structure in the Y direction using acceleration-based pushover in Y direction at a lateral deformation of 225 mm. So we will define the pushover load cases. So to do that, we will first need to define the gravity load case in the form of a nonlinear static gravity load case. So we'll go to define load case. We will name this as gravity. It is important to note that the case type must be selected as nonlinear static rather than linear static, because we are going to run a nonlinear static pushover. And all the loads that has been applied on respective frames at each level must be specified and added into this load case. So we have dead load, slab, metal deck, curtain wall, floor, SDL. This dead load accounts for the structural weight of the structural members, the self weight in particular. So an appropriate reduction factor in the form of a scale factor for the life load must be specified as well. So once this is done, we will then add a new pushover load case. So we will call this as push Y, because we are pushing it in the global Y direction, in the direction in which the frame has been modeled. Push Y, and we will do a acceleration-based pushover. The load case type, as mentioned, is nonlinear static. We will start the push from gravity. The load type is acceleration because this is an acceleration-based pushover. We are pushing it in Y direction. So by default, UX is selected. We must select this to UY, which is global Y direction. The scale factor, if you are specifying a push load case, you can either specify 1 or -1, but the other cycle of pull should be the opposite to the scale factor specified for push Y. For example, in this case, we will specify scale factor of -1 for this acceleration push case. For the pull case, the scale factor will be +1. The next step is we will do a displacement control. So we will go to load application, modify. We will select load application control as displacement control. As discussed earlier, we will be pushing the structure at 1.5% drift, which is 225 mm at the reference node, which we have initially specified, which was at the top right of the roof level. So we will be pushing that node to 225 mm, which is actually 1.5% drift. U1, so monitored displacement, we are pushing the structure, we are carrying out pushover analysis in Y direction. So like I've mentioned earlier, this must be U2 rather than U1. U1 means analysis or pushover analysis in X direction. So it is important to note, if you are running a pushover in Y direction, the degree of freedom shall be selected as U2. The label of that reference node, initially, the unique name was 224 and the label was 4. So we will specify the right joint label and the story 4. That's the topmost level of this 2D frame. Final states, the results that will be saved must be selected to multiple states and can be specified as 10 or 20 to get that nonlinear pushover curve. Once we have defined the push Y acceleration load case, we also have to define the pull Y acceleration load case in order to plot the hysteresis of the structure and to estimate the area-based damping following the half-cycle nonlinear pushover analysis. To define the pull Y acceleration load case, we will go to define load cases. We'll make a copy of the push Y acceleration load case. So click on push Y acceleration, add copy of case. We will modify this to pull Y acceleration. The start of this load case will initiate from the last step of the push Y acceleration load case. And the scale factor for this should be the opposite to whatever we have specified for the push Y acceleration load case. So for the push Y acceleration load case, we have specified the scale factor is -1. So for pull Y, it will be +1. The other parameters remains the same. We'll click OK and then run the analysis. Once the analysis is complete, you can go to display, show static pushover curve, and obtain the pushover curve for the two load cases. So for the push Y, the pushover curve is shown. So you can extract the load deformation data by clicking on this grid, go to formatted, and for the number of steps that we have specified for this load case, we have specified 20. So the monitored displacement and the base force for the 20 steps can be copied from here and plotted as a graph in Excel. We can also plot the pull acceleration in Y direction. You can click on pull Y. And copy the monitored displacement versus the base force. and then we can plot it. By plotting these to push and pull load cases, we can obtain the hysteresis of the structure for the half cycle analysis. So the cyclic pushover curve gives you a hysteresis or the area-based damping of 45.65%. Now, one important thing to note here is that if you go back to the push Y acceleration load case, then we will observe that the system remains essentially elastic till 33 mm, 33.75 mm lateral displacement, where the force is approximately 1,946 kilonewton. So if you are tuning the DMAX, it is important to note where actually the nonlinearity in the system starts from. So here, looking at the pushover curve, we know it is the nonlinearity initiates after 33.75 lateral deformation. So this is the slip of the 2D frame. And this is at step, if you go back to the formatted time step, we will see that this is occurring at step 3. So to look at the individual link performance, like where exactly the link slips, we will need to go to the undeformed shape and just click on the link, right click, you will be able to see the unique name of this link. It is K1. So you can also go to this tick box, click on that box, go to other assignments. Under link assignment, if this unique name is not checked in, you may tick this in to view the unique name directly on the model. So at level 1, the DMAX unique name is K1 and K2. So we will go to display quick hysteresis link, and we will go to step 3 where the system slip was obtained. And we can see in push Y at this point, level 1 link is still behaving as a linear link. So what can be done here is slightly reduce the capacity of the link to ensure the slip of the system and the slip of the link at that level is at the same time. So that concludes the modeling and analysis video for today. And I hope you have learned how to model the DMAX in series with the braces and perform a nonlinear static pushover. If you have any further questions, please do not hesitate to reach out to the Tectonus team. Thank you.